Thanks a lot for the introduction. Very happy to be here. I am Ranvir. This is a joint work with Sreeram, Kannan, David Say, and Pramod Viswanath. First of all, let me you give a very good motivation for sharding. But let me just start off with the main problem in blockchain. I would say layer 1 blockchain. It's a blockchain trilemma. So we want decentralization, as in we want nodes to join in whenever they want. We want nodes to have no identity on the blockchain, ideally. And we want security, as in we want security against static adversaries and adaptive adversaries that can corrupt nodes based on a certain budget. So you will notice that proof of work blockchains like Bitcoin and Ethereum, which rely on full replication, achieve these two properties. But because they rely on full replications, they're not scalable. And scalability, we mostly think of 3 axes: storage, scalability, compute scalability, and bandwidth scalability. Now, there has been a lot of work, and they're not scalable because they rely on full replication. There's been a lot of work both on the academic side. Examples are OmniLedger, Elastico, Rapid Chain, and Gearbox, which is a new protocol from you guys. And there is also a lot of industrial interest in this. Ethereum is proposing sharding, there's Zilliqa, Polkadot, Cosmos, and so forth. So, that's basically the motivation behind it. Now, the way sharding works, a very high-level picture of how sharding currently works in most protocols is you divide the ledger into k shards and assume that these k shards have exclusive state. And once you divide this into k shards, you run each shard as a separate blockchain, as in you run a separate consensus on each of these shards. Now, because you're running separate consensus on each of the shards, you want each shard to have an honest majority or supermajority based on what the consensus protocol is. And in order to do that, you require an allocation, a committee allocation mechanism. So basically, you have, let's say, 10,000 nodes. And you know that of those 10,000 nodes, like 3,000 are malicious. But if you're splitting it into like small shards, small committees of 10 nodes, for example, it is very difficult to ensure that those 10 nodes are the 30% adversarial fraction translates into those 10 nodes. That 3 of those 10 nodes are adversarial and no more, right? So in order to ensure that, you require, first of all, some sort of randomization of the allocation of this global committee, global mining power or global stake or whatever the system is. You need a way to randomly allocate validators or miners in that global system into small system. So you require randomization and you require large enough shard sizes so that adversaries are proportionally, or honest nodes are proportionally represented in this k shards. As I mentioned, you run in multi-consensus. There's a separate consensus algorithm for all of this for each individual shards. And because each shard is only maintaining a subset of the state, and they're only maintaining a small portion of the transactions, small portion of the ledger, you achieve scaling. If the ledger has 4 shards, k shards, then each shards only maintains k fraction of the state. It only runs k fraction of the transactions, and it only communicates k fraction of the total payload. So this sounds very simple. So why are there a lot of papers on sharding? Well, there are a few problems with this approach, which we call multi-consensus. As I mentioned before, first is to ensure proportional representation of honest nodes on shards, you require large shard sizes. And because you require large shard sizes, that inherently limits the amount of scaling that you can achieve. Within a shard, there is still full replication. So if the shard size is, let's say standard is 100, you still have a single transaction being repeated 100 times in 100 computers. Another drawback is security. So these systems have a beacon chain which generates randomness and which maintains this node to shard allocation algorithm. And at regular intervals, it basically randomly allocates the global committee into shards. But within a particular interval, if that adversary is adaptive, it can corrupt, it can target a particular shard and corrupt a majority of nodes in that shard. So a simple example for such an adaptive adversary would be like you can just post a transaction on a simple chain saying that a bribery transaction on another chain saying that, hey, if you allow me to control some transactions on that shard, I'll pay you this much money. So it's easy to bribe nodes in a particular shard, and because the shard size is small enough, it's very easy to attack a single shard. And a safety or a liveness violation in a safety violation, especially in a single shard, can affect through double spends all other shards. Now, the solution to that is typically adaptive is you allocate this, you randomly reallocate validators frequently enough that the adaptive adversary doesn't have time enough. So you adapt faster than the adversary, which is something which comes with high computational cost for honest miners, because every change in shard would lead to a few more computation because you need to sync to the new shard that you're going to. And because of this reason, we say that multi-consensus architectures are not resilient to order 1 by k adaptive adversaries. So you only need, if you have 1,000 shards, you only need one, like 0.05% of adversaries to target a particular shard and break its safety or liveness. And another major drawback is you require node identity, because you run this node to shard allocation algorithm, which takes a global pool. In order to get that global pool, you need to know what are the consensus nodes participating in the complete system, and because of that, we say that the identity of consensus node leaks into the system before they participate in any consensus decision. So if you take, for example, Bitcoin, you don't know who the proof of work miners are before the mine block. So the identity is not revealed before the mine. And we believe this is an important property which is not seen in this committee and node to shard allocation based sharding algorithms. And because you require identity, you also cannot allow dynamic availability. And the existing sharding solutions don't support the adaptive adversaries. But they can achieve both or all the scaling properties of storage, compute, and bandwidth. A solution to that, so basically we need to solve identity free. Making identity free will also help us solve dynamic availability and adaptive adversary properties. So for identity free, if the sharding is identity free, we would have to, we cannot use node to shard allocation algorithm, as I mentioned before. So if you don't have this allocation algorithm, your only choice is to allow nodes to self-allocate. And the problem with self-allocation is, well, if you're allowing self-allocation, why can't just adversary congregate on one shard and break its safety and liveness? And because of that restriction, we need to define a new architecture, which we call a uniconsensus architecture, where the consensus or ordering happens through a single chain which everyone maintains. It's a lightweight consensus which everyone maintains, and that defines order of all the shards, as opposed to a separate consensus algorithm for all shards. So there are a few building blocks to this uniconsensus architecture. One of the fundamental is you decouple transaction validity from transaction order. So because you don't want ordering is done by everyone. As I mentioned before, this single consensus ordering is done by everyone. You don't want everyone to validate or receive all of the transactions. And because of that, you need to decouple ordering from validation. So once you have order, it's deterministic to validate transactions. This is a popular approach used in many protocols such as Prism, which achieves high scaling, Lazy Ledger, which relies on a similar uniconsensus architecture, and it creates a sidechain from it. So you have decoupled validation. Another main building block is sortation. So this mining sortation basically ensures that a single node can only mine on one shard of its choice, a shard of its choice, but one shard, and it effectively partition. It cannot focus on whether mining on a shard or mining on a proposal blocks. So for time being, for this presentation, I'll just assume that we are running on proof of work. However, the protocol is agnostic whether we use proof of work or proof of stake. So this is a proof of work sortation. So proof of work sortation runs by creating a meta block with a particular. You fix the shard ID before mining, and based on where your target is, you either mine a block which corresponds to consensus, the single global consensus. It's called a proposer block, or you mine a shard block, which is a payload block which contains transactions for a shard. Now, this is different than, for example, if you might have heard of monoxide, which also claims to do proof of work identity-free sharding. But in monoxide, a node can mine on multiple shards at once. A single successful mining can lead to creation of blocks on multiple shards, which is something which we don't allow because we want scalability. We assume that a single node can only maintain one shard at a time. Okay. Right. So this architecture has safety because ordering is defined by the proposal chain, which is supported by the global mining power. And the ordering of each shard is dictated by this proposer chain. So you basically add a hash reference to shard blocks inside a proposal chain and use that hash reference to create the ledger of each individual shards. So as a node, I maintain a particular one shard, and I've also maintained the proposal chain. And because it only maintains a hash pointer, it's relatively lightweight. Okay, so now we had safety properties. We are safe even if a particular shard has more adversarial miners. But you have a liveness vulnerability, which is if a shard has a high concentration of adversarial mining power, then most of the shard blocks proportional to the adversarial mining power mined for that shard will be mined by adversaries, and the adversary can effectively censor transactions on that chain. And because of that, it can lead to a reduction of chain quality in that target shard. And a reduction in chain quality will effectively correspond to a reduction in throughput because you have to limit the rate of shard block production because of resource limits. So because you limit the rate of shard block production, any censorship attack would lead to effective reduction of throughput. And in the worst case, an adversary can focus on just a single shard and reduce its chain quality to a fraction equal to 1 by k. K is the number of shards. Okay, so in order to solve this, we would require honest nodes to adapt to adversaries and allocate themselves to new shards based on some observation that they get from the main chain. Right? Ideally, we want honest nodes to allocate themselves to shards which are under attack. In simple words, there's a simple way to do this. Let us assume that an adversary's past allocation are known, and let us treat this thing as a game. So at a particular time step t equals to 1, you observe the adversary allocation. You see that the adversary is now concentrating on shard k. In the next time step, honest nodes reallocate themselves proportionally to how how the adversary was allocating itself to this particular shard. And you basically repeat the allocation of adversary in the previous time step. And so this is kind of a myopic policy. And we show that this policy will have a worst case shard chain quality of order 1 by log k. So this is an improvement from order 1 by k to order 1 by log k. However, and we show that there is an adversary, there is an optimal adversary which can attack the system. The optimal adversary basically works by gradually increasing its mining power in a particular shard by a factor of log k in every epoch, and cyclically adapting its concentration in that shard. Now, I assume that you know the adversary allocation in a particular shard. However, you don't know which node is adversarial and which node is honest. So in practice, you don't need to know the actual adversarial implementation, allocation. You only need to know the total mining power in a particular shard. If you know the total mining power in a shard, you know what the DSA policy is, you know how honest miners following the DSA will allocate themselves to the shards, and then you can just, based on that, estimate the adversarial allocation in individual shards. So the best we can achieve, there's an information theoretic bound which says that the best you can achieve, the best worst case performance you can achieve is equal to the chain quality being equal to the global honest mining power. So which is order of 1. Remember, in simple DSA, we only achieved order 1 by log k. So the way we Free2Shard achieves this is you don't have a myopic policy, but you have policy which observes the total average long-term chain quality in a particular shard and allocates itself proportionately based on this long-term chain quality. So if a shard is lagging, if its average long-term chain quality is lagging this global honest mining power by a certain amount, you allocate that proportional to how much the lag is. And if you are ahead of the global honest mining power, you don't allocate to that shard. So we change the policy from myopic to long-term. And we show that this policy performs arbitrarily close to information theoretic bounds, which essentially says that now over a long term, the chain quality of even the worst performing shard is equal to approaches the same value as the total global honest mining power. And we model this as a Stackelberg game between adversary and honest nodes, because we assume that adversary can always view what steps honest miners are going to take beforehand, before making its own move. And the adversary can allocate reallocate instantly to new shards. And the proofs of this have parallels with the classical Blackwell approachability problem. We show in our simulations that we have a convergence, that we converge to this to the ideal chain quality of in our systems. We had ideal chain quality of 0.5 pretty fast. We prove that the convergence is order 1 by root t. T is the number of timestamps in which this self-allocation happens. So it's pretty fast. So within 30 reallocations, your chain quality attains the target. There are also some very interesting properties that our algorithm will have. For example, you can support systems where your number of shards is greater than the number of nodes. So you can imagine like a system with 1 million shards and 10,000 nodes, and we can still support chain quality equal to n by k, which is the best you can achieve. We also support heterogeneous sharding. So we can support different throughputs or different chain qualities in different shards by appropriately adjusting the target value in our DSA algorithm. Other advantages are, we allow slow allocation. So honest nodes can allocate at much slower rate compared to the adversary. As I mentioned before, we assume that the adversaries can adapt instantly based on seeing the honest behavior. we also allow partial honest participation. So we don't require all honest nodes to follow this DSA policy. Even if a small fraction of honest nodes follow DSA policy, we can still achieve the required goal. Right. And we also developed this system on a Rust code base, on a full stack Rust code base. So a few things when you are integrating this complete system is you need to make sure of a few problems which are standard to, I guess, most sharding solutions, such as data availability and state commitments. So you require, so validation, once the order is decided, validation requires you to know what exactly the transactions are that correspond to the hash pointer. So you need the shard blocks to be available. And the reason it's challenging is because you need bandwidth efficiency. Not all honest nodes will receive all shard blocks. They will only receive shard blocks of their own shard. So to achieve this data availability scalably, we implement an existing solution called coded Merkle trees. Similarly, for state commitments, the reason you require state commitments is for nodes to self-allocate to a new shard, you need it to bootstrap to the new shard. And you require this bootstrap to happen efficiently. And you can achieve this by maintaining state commitments, which and just transferring state when you allocate to a new shard. State commitments are a bit challenging in our protocol because we have decoupled validity. And because we have decoupled validity, our state commitments require a verifiable computing framework. So for now, you can use ZK snarks, or you can, right now we are using true bit style interactive verification game, where a particular node, some randomly chosen node posts a state commitment, and there is some interactive game which validates whether that state commitment is correct or not. Right. So this is our overall architecture. Just to recap, the consensus engine is maintained by all nodes. It's lightweight, only has hash pointers to shard blocks, and a single node only maintains, a single honest node only maintains one shard through the shard logs. And we have dynamic SA to allocate, to suggest to an honest node which shard to allocate to. We have a system implementation built on top of Prism proof of work consensus algorithm. We implement that over 3,000 lines of Rust code. We have a dashboard. Because Prism is high throughput by itself, we were able to achieve, just using 6 shards, we were able to achieve a throughput of 250,000 transactions per second by running these experiments on AWS C5D.4x large nodes. And we show that there is almost near linear scaling with the number of shards. The reason why you can achieve this like 100 shards with slow number of nodes is because you don't have size requirements on a particular shard. So you can have a shard with very low number of nodes. To summarize, now our protocol is identity free. It has dynamic availability. It's secure against adaptive adversaries. You can have adversaries move instantly across nodes. You can handle large number of shards. You can have asynchronous shard rotation, and you only require small fraction of honest nodes to run DSA. And this is my last concluding slide. So in Bitcoin, you have good security against both adaptive adversaries and static adversaries, but you don't have any scaling in communication, computation, or throughput. With multi-consensus architectures, your throughput scales, but you no longer have security against adaptive adversaries. In a uniconsensus without dynamic self-allocation, you have security against dynamic adversaries, but your throughput doesn't scale because a worst case shard will have a throughput of 1 by k, and that multiplied by k, total number of shards, will give you throughput order 1. But in Free2Shard, we can scale both throughput while maintaining resilience to adaptive adversaries and having this whole system identity free. That'll be all from my end. Thanks a lot for your time. Happy to answer any questions.